Another way you can store values in memory is using a stack. Yeah. So I'm going to set this up a little differently. Let's say down here in our print function, let's just go ahead and make it so it prints the numerical values. Here, so here I'm using quotations. Seems like most people just use you can do it this way as well. It's easier to type. I just seem to prefer hitting shift and using quotations when I do it. So I'll stick to my paradigm. You stick to yours. All right. So now this should print numbers, but it will not print a value higher than 9. 0 to 9 only, or it'll print some other weird character. So for the purposes of our demo here, let's say we have a situation, we want to print a character and then or do something in code, and then later on we want to print that, fetch the value, do it again, But then in between we have something that messes up whatever we have stored in memory. Okay, here I'll even go so far as to just let's just wipe out AX entirely for demo purposes here. AX, okay, there. So we know whatever was going on in the code is going to get destroyed here, but we want it back again there. Okay, so a quick way to store things in memory is push and pop. Okay, and you can push a value into a place in memory and then pop it back out onto the stack, and yeah, stack is what it sounds like. It's like a pile of memory. Okay, we'll talk more about that when we do it. So here, I could go push Al, but the problem actually here is we're calling another function, and when you go down in the function, it messes with what's in A and stuff too, so might be wiser instead to copy the data to the stack up here before we call print, right? And then I can do my destructive code, and then down here I don't need to move. I can just not pop app, sorry, pop Al. Well, I should just type it. It's 3 letters instead of copying and paste it. Like I said, it prevents spelling errors when you copy and paste more. Okay, so pop Al, that's all I need to do. There. Let's try that. Oops, I closed my thingy there. I need to go get my path. Yeah, and we'll NASM and QEMU that. 8 invalid. What did I do? Push out. Got it. My bad. I can't just push the 8-bit value here. So good illustration. This is what I wanted to do. I can't do it that way. I have to. I can only push the entire 16-bit value, so I have to push AX in there, and then I can pull AX back off the stack. There. Good lesson, I hope. Let me save that. There. 232. You see. That is push and pop. And we are pushing things onto the stack. Now, another great thing I could, like if I'm working with an entire deck of cards, I'm making a card game or something, I could put 52 things on there. I could put like 35,000, somewhere in there, things on the stack. But here's the thing. Let's say I'm going to push a bunch of things onto the stack here. Here, let me go up in here. We'll go character value. There, I'm not going to print it. Okay, so first character will be 1, second one 2, second one 3. There, and we'll push several things in a row onto the stack. And then down here, let's forget about this bit here. We'll just go pop it and print it, and we'll do that for the rest of them there, and have a look at what's on the stack. Okay. 3, 2, 1. There you go. So, keep in mind, this goes way back to the early days when all you had was your 4 registers, A, B, C, and D, right? And, of course, if that's all you got to work with, you can quickly run out of space, So some programmers are like, yeah, I need somewhere where I can take some of these values and store them while I do something else, and then, retrieve them, and so some engineers like, oh, no problem, I'll just make a circuit where you can throw everything onto the heap, and then when you want it, you have to pull it out in reverse order, right? I don't know whose brilliant idea what that was, but I'm sure you can take a wild guess, right? So the other thing about a stack is I can also tell it where I want that stack to be in memory. Let me see. Down here after origin, I guess is a good place to do that. And the way you do that, first, let's, I don't know why this is distracting me. Move AX, we're just going to tell it where in memory we want our stack to begin. That will be OX9000, as you know from the previous, here. There's our origin, so I'm saying start our stack down here somewhere where it won't interfere with our current code. And move SS, the defining where our stack begins. So, oops, move SS there. Excuse me, comma AX, this value. Okay, so I have set our stack. All right, okay, where it begins in memory, and then we want to set the index value. Remember, a segment offset, right? So now we want to say where the offset is. That is move stack pointer. Okay, and this is backwards, of course. So you start from the last first, right? So the stack is, of course, an example of LIFO. LIFO, meaning last in, first out. Right? You have a deck of cards, and you're laying a bunch of them face down on the table, and then you want to start pulling them off again. You take the last one off first, and so you're working backwards. So that's the way your stack works, or last in, first out. Okay, there. That is stack. Of course, this is pop and push and pop stacks. You probably don't use these in higher level programming languages, but you see it all the time in assembly for this reason. Because you run out of room, you have a limited amount of memory, you want to store it somewhere and retrieve it, and then that saves you having to go and name, specify places in memory. Here, of course, I've specified a place in memory for the entire stack, and then that way I could have more than one stack. I could have a stack of cards over here and a stack of something else over there, and call them by name or number, you see. Okay, I think I have covered all the bases on stacks then.